So, um, I apologize that this is how we're going to have to do it. There would be, it's the least favorite way I've ever given a video or given a lecture. I'm not enjoying this, and I find it uncomfortable, as I'm sure you do, to watch it. I'll also apologize for any lack of quality. It's being done on a iPhone in a laboratory on the third floor of the science building here at USM. And hopefully it will be enough to provide you with those things that we missed. Our problem obviously is that we simply have to keep moving. We can't just miss 4 classes and think that the course is going to get completed, that you will acquire the information that this course really requires you to acquire. Otherwise, it's not the chemistry course you wanted to be taking. So I'm going to talk about those things in chapter 3 that I was meant to get through during the course of this week. So the Tuesday lecture, the Thursday lecture, today's lecture that we missed this morning, I am speaking on the afternoon of Thursday. Hopefully in this I'll get through chapter 3. I may stop and break it up into 2 pieces. We'll see how this goes. It's very likely that I'll do it in less than the 2 times an hour and 15 minutes that a lecture would be. I'm going to be succinct. I'm going to go to the point. I'm going to hopefully not skip anything, and you're going to be responsible for what I am about to tell you. And I wish there was a better way to do it, or that we could avoid this. But you will be responsible for it, and I will hold you to the standard of someone who went to class, was in the lecture. So let's start. The last thing we talked about, the last class that we talked way back whenever that was, we were talking about ionic bonding and how that involved a metal and a non-metal, the transfer of electrons from the metal to the non-metal. We acknowledge that that's a bit of a simplification, but it's good enough for this course. It's accurate enough for this course, and that what we end up with is a cation and an anion, a positively charged species and a negatively charged species, and that they're static charges, they're non-moving charges, are opposite, and so they stick together really positively. And those strong electrostatic forces lead to all those physical properties you're familiar with, that it's brittle and a crystal, high melting point and high boiling point, because the electrons don't want to move. The sodium's given up its electron. The chlorine has become chloride and is happy as well. Neither of these want to evolve, give away, gain electrons. So no electrons move, no conduction of heat, no conduction of electricity. Most recently, we started to talk about covalent bonding, about the sharing of electrons. And this entirely involves nonmetals. So those nonmetals are in the top corner of the periodic table, up there in the top, if you look at it, top right, carbon, nitrogen, oxygen, hydrogen, phosphorus, and sulfur are really the elements we're going to be talking about. Because we're biological chemists, we like to talk about the chemistry of biology. So we're going to be talking about those species specifically. We're going to talk about covalent bonding. And so what we know is that it's the opposite of what you've been told about ionic bonding. Instead of electrons transferring from one species, from one atom to another, they're going to be shared. And we talk about, you should refer to the PowerPoint slides that you have on Blackboard, and we're in chapter 3, of course. And you should look at those PowerPoint slides, and you should look at the description of covalent bonding. We talked about the octet rule and about how this really involves the outer shell, what we call the valence electrons. Only those are involved in this chemistry, and only those elements that are nonmetals, that don't want to give up electrons, that want more electrons so that they can fill up that octet. They can be perfect, like a noble gas is perfect. They all want to aspire, they all aspire to that noble gas octet. So carbon is in group 4. If you have a periodic table, while you watch this, which I'd recommend, you'll see that carbon's in group 4. What is carbon's ambition? Well, carbon could lose 4 electrons, or if it was metal, hypothetically could gain 4. There's in fact a carbide that exists, but more likely it's going to want to share. And we looked at the simplest example of covalent bonding, methane, or methane if you're from England. And methane involves the sharing of 4 electrons with 4 hydrogens. We use this, what's called Lewis dot notation, to indicate that. You'll notice, if you can see this image, that in that image, carbon has 8 electrons, that each hydrogen has 2, like, here I come, and it's backwards, but each carbon has 8 electrons around, the carbon has 8 electrons around it, each hydrogen has 2. So everyone sort of fulfills that noble gas ambition. Hydrogen has the same number of electrons as helium, a noble gas. Carbon has 8, like neon, again, a noble gas. So everyone's fulfilled that ambition to be perfect, if you will. Now, we can make all kinds of molecules like that. We talked about, and you have in your notes, ammonia, which is in group 5. And there's a consequence to being in group 5, and that is that those 5 outer shell electrons mean that there's 2 that exist without pairing to another atom, right? So we have nitrogen making 3 bonds with 3 hydrogens. And then there's this lone pair. Remember, the lone pair is that unshared with any other element pair of electrons in a lone pair. So an oxygen does that as well. Oxygen has 6 electrons, so logically, if it makes covalent bonds with another nonmetal, like hydrogen, it can have 2 lone pairs and 2 paired with hydrogen, H2O. And we talked about how that informs its geometry in 3-dimensional space, that it has 4 things around it, like carbon does. Carbon has 4 things around it, 1, 2, 3, 4. Nitrogen has 4 things around it, but 1's a lone pair. Water has 4 things around it, but 2 are lone pairs. So water has 2 bonding pairs with hydrogens, and then 2 lone pairs, right? So carbon, nitrogen, and hydrogen and oxygen really share that chemistry. Think about it. They all have 4 things around them. It's just that carbon has 4 bonds, nitrogen has 3 bonds and a lone pair, oxygen has 2 bonds and 2 lone pairs, but everyone has 4. So, and again, you should look at the slides on Blackboard to look for these. We talked about how we can have the anion in a salt can be a covalently bound species, especially some nonmetal bound to oxygen, which will change its name. So sulfide is, sodium sulfide would be Na2S, sulfide by itself, sulfur by itself. But sodium sulfate would be Na2SO4, the A suffix of the nonmetal, indicating that it's bound to oxygen. And remember, as the slides say, that you should and must look at, that no one's going to ask you to memorize these polyatomic, many atom anions that could form salt ionic species with a metal. But you should know at least that 8th thing. And we talked about the diatomic elements like hydrogen, and then going that backward 7, oxygen, nitrogen, bromine, chlorine, fluorine, chlorine, bromine, iodine. So there are 7 diatomic elements. So why are they diatomic? Everyone wants to fill that outer shell. You should always be trying to get those Lewis dots to make sure that they always have 8 around them, except for hydrogen, which wants 2. So there's a good slide that has a quick review. In fact, I'm using my Christmas present clicker to watch the PowerPoint right below me, right in front of me here. So I'm looking at the slide you should look at, a quick review of ionic and covalent bonds, which talks about this transfer of electrons from metal to nonmetal, which involves hand moving for some reason, or the sharing of electrons in covalent bonding. And that really is going to be an exam question. So you should know ionic and covalent bonds, metal and nonmetal, transfer of electrons in ionic, only nonmetals, sharing of electrons in covalent bonds. And that really, once we know what ionic bonding is and how it works, we're going to leave it aside. Remember how we said that about neutrons and protons? Same true for ionic bonding, because you and I care about carbon and living things and biology and the chemistry of life. I will say that the textbook never mentions what's called metal bonding. What is metal bonding? Well, remember, there's a central idea here in chemistry, which is that things only bond because they have some reason to do so. They don't stick together because there's no external deity, if you will, sticking Legos together. They have to have an ambition to do it. And you think to yourself, well, I can see why ionic things would stick together. You know, they're oppositely charged now. They stick together like magnets. I see why covalently bound things could form bonds, right? It makes sense that hydrogen wants 2 like helium, oxygen needs 8 like neon. So why is copper solid? Well, the text never mentions this. The text never talks about metals and what we could call metal bonding. But it's really kind of cool. So here's what I want you to picture. You've got a lot of copper atoms. And remember, you know, what we said about metals. Now, what I want you to understand about metals is that what defines them as metals is loosely held electrons. Electrons they don't even want. Electrons that they can float away. And all the metals have this characteristic. Iron has electrons to give away. Copper and neon, not neon, nickel and cobalt and chromium and zinc and all aluminium and calcium and magnesium in the group 2, the alkaline earth metals. All of them have electrons to give away. So picture and I would look at the slide for this because I'm not going to do any drawing referencing this. So the next slide is that about metal bonding and about how there are all the nuclei, Latin plural, all the nucleuses of coppers, lots of coppers, protons and neutrons, right, in the nucleus, lots of them. So what's the force holding them together? It's a strong force, isn't it? Because copper has a pretty high melting point. Well, what is it? Well, here's what it is. All the nucleuses, imagine them all lined up in 3 dimensions. And they're all positively charged, and there's lots of protons in copper, right? And lots of protons in iron, 26 in iron. Lots of protons in these metals. And then these loosely held electrons. So picture, if you will, a table. Let's just do 2 dimensions. Copper in front of me. And all these electrons, and they're all moving. They're all washing because electrons are loosely held. And they're washing. They're just moving around, right? And so this copper nuclei is attracted to that electron, that electron, that electron, that electron. And then it's attracted to that electron, and this nuclei, all the nuclei are all attracted to all these different electrons, right? So they're all grabbing hold of oppositely charged electrons. And the electrons keep washing over and getting attracted to different nuclei. And that oppositely charged sharing of loosely held electrons is why metal atoms stick together, because they're all attracted to all these loosely held electrons as the electrons wash over it, right? They conduct heat, they conduct electricity. And that sharing of those loosely held electrons, they're all attracted, right? Nuclei are positive, electrons are negative. They're all attracted to them. And so that's metal bonding. And the good thing about metal bonding is you should know what it is, and you should have heard about it, and then we'll stop talking about it, right? We'll stop, I won't ask you, why is magnesium a solid? Although you could talk about this cloud of loosely held electrons that wash over, and all the nuclei are all looking at these electrons and trying to grab them because they're absolutely charged, but then they keep moving because they're not that well held on, right? That's metal bonding, and you should have heard about it even if the text apparently just ignores it entirely. Next in your PowerPoint, in chapter 3, is a bunch of questions. What types of bonds do the following form? Well, all you need to know is whether it has a metal, right? And this is a very famous test question. What kind of bonds do the following form? Well, CH4 is carbon and hydrogen. They're not metals, so only covalent. Magnesium and fluorine, magnesium fluoride it would be called. Well, magnesium's a metal, so that's an ionic bond between the magnesium and the two fluorines. Ammonia, NH3, we've seen that in fact. There it is behind me. Ammonia is NH3, right? It's got a lone pair up there, and it's got 3 bonds, 1, 2, 3. This is harder than it looks. And so it's all covalent. There are no metals in it. Basically, this question is, are there any metals, right? So potassium NO3. Well, what would you call that? Well, potassium's the cation because it's a metal. We know it's ionic bonding. NO3, well, if the N was by itself, it would be potassium nitride. But because it's attached to oxygen, potassium nitrate. And I want you to be able to do that. Chromium and chlorine making this bond, chromium chloride. It's an ionic species because it's got a metal. And CO3, ooh, what is that? Well, it's all non-metal. It's some kind of polyatomic mini-atom anion because it's got a charge. An ion, by definition, is anything with charge. And so this is called carbonate, and that's a carbonate anion. Characteristics of metal, well, we have lots of them, right? Can be pulled into wires, can be pulled into sheets, it can be, will conduct heat, will conduct electricity. High, on the whole, high melting points, all but one, all except for mercury is a solid at room temperature. An ionic molecule, we've done that many times. In covalent molecules, it's kind of a trick question because everything, nearly everything around me is covalent. There's no definition of covalent character. Water is covalent, but so is my shirt, right? What do paper, wool, plastics, trees, badgers have in common? Carbon, right? Carbon is going to be the answer to a lot of questions in this course going forward because carbon is living biology. Biology, carbon, really, they are inseparable. What type of bonding is it in all diatomic molecules? Well, it's covalent bonding, right? It's always non-metals. Oxygen, nitrogen, fluorine, chlorine, bromine, iodine, and hydrogen. It's always the pairing of non-metals to fill their outer shell. They're all molecules that by filling their outer shell and sharing electrons, they are comfortable. And so they float around as elements, as gas elements in pairs. And the Lewis dot structure for oxygen fluoride and ammonia, I'll leave that to you. You should be able to do that. So I'm going to stop here because I want to see what my video looks like, whether I wasted 18 minutes and 39 seconds, and then I'm going to start talking about the shapes of molecules. Not trivial, a bit difficult. So you should go find the second video in this sequence. It's going to start on the PowerPoint slide about geometry and shape. And it's not trivial. You may want to watch the next video 2 or 3 times. All right.